Hello, this is Dr. Webb, and in this video we're going to talk about one of the most important and most used applications of derivatives, and that's finding maxima and minima functions. Okay, so when we say a relative maximum, sometimes called a local maximum, occurs at some point AF of A, if for some interval centered at A, all the x around there, the value of the function at x is less than or equal to the value of A. So if we're thinking about this, we have some point A f of A. So the x value is A, the y value then is f of A. Well, then what does the function then have to look like on either side of this? Well, there's some interval, A's in the middle, such that everywhere else on here, the function value has to be less than this spot. So has to be going down on either side. Okay, and so that's a relative maxima. On the other hand, a relative minimum occurs at a point where at all the points around it, the function values are higher. So here's where our relative minimum is, b f of b, and then, so if we think about this as being the x-axis, there's b. We have some interval such that for everywhere else on this interval, the function is above it. Okay. So that's relative minima. Okay, so if you look back at both the relative maximum and the relative minimum we drew before, right at that spot where it's occurring, f of x can't be increasing or decreasing, right? So for a maximum, it's going like this. That's an ugly hitch in there. Let's get rid of that. Okay. So our maximum would be right there, say. Well, if you look, it's increasing to the left, decreasing to the right, but right here in the middle, it's neither increasing or decreasing. In fact, it's switching from one to the other. On the other hand, for a minimum, on the left here coming in, the function's decreasing. To the right going out, it's increasing. But right there at the spot where the minimum is, it's neither increasing nor decreasing. Right? So what does that mean in terms of the first derivative? Well, that means that either, since it's not increasing or decreasing, if it exists, the first derivative has to be equal to 0. And then the other option is just that it doesn't exist. Okay. And so here's some basic examples. So here is a relative minimum first. And if you drew the tangent line here, it'd be flat, slope 0. For the relative maximum here, again, we have a flat tangent line. And then for this third example, we have a relative maximum right here. If you look coming in, the slopes to the left are pretty positive, slopes to the right are pretty negative, and they don't match up at that point. And so for this one right here, f prime of x at this point doesn't exist. So this is an example of what it would look like when it doesn't exist. Let me erase this so you can get a clear picture of it again. And so you can see it kind of comes together as a hard angle. And so we call that, the fancy math name for this is it's a cusp. Okay, so this is the example we had from the last video where we were looking at increasing, decreasing, concave up and concave down. For this one, let's just look at where the relative maxima and minima are. So where are the relative maxes and mins? Okay, and so looking at this, these two spots right here, you can look at intervals around those points. They are the lowest point of the function on those subintervals right there. And so that makes both of these points relative minimums. And since minimum comes from Latin, its plural is minima. On the other hand, if we take this point right here, we can make a little interval around it and see that it is the highest point on its interval. And so that makes this point right here a relative max. Okay. So to find these relative minima and maxima, what we're going to look for is points that are called critical points. And so what a critical point is it's a place where the derivative is equal to 0 or the derivative doesn't exist. Right? And so the idea of this is that this is coming straight from the idea of what has to happen at a relative min or a relative max. Well, either the derivative is equal to 0 or it doesn't exist. So the maxima and minima have to occur at a critical point. If a point is a maxima or a minima, it has to be a critical point. Now, on the other hand, not every critical point is necessarily a maxima or minima. And so right here we have a graph of a cubic, kind of like x cubed. So you can think about this as roughly being y equals x cubed. And if you look at this point right in the middle, draw the tangent line there. The tangent line there is horizontal. So f prime of x there is equal to 0, but is that a relative max or relative min? No. To the right of it, it's increasing. To the left, it's increasing. So to the right, there's points that are higher. To the left, there are points that are lower. So it's neither a max nor a min. So this is a critical point, but not a relative max or min. So not every critical point has to be a max or a min. The definition for critical points, we're looking for where the first derivative is 0. Okay, so let's do a quick example. Here's a cubic, minus x cubed plus 3x squared plus 9x minus 4. Let's find the critical points for this cubic, right? So looking back, it doesn't exist. So we want f prime of x to equal 0 or not exist. So what's the first thing we got to figure out? We got to get the first derivative. So this is a cubic polynomial, just using the power rule over and over again, not too bad. So we get minus 3x squared plus 6x plus 9, and then the minus 4 goes away. So that's our first derivative. Next, we're going to set equal to 0. So 0 is equal to minus 3x squared plus 6x plus 9. I can factor a minus 3 out. X squared minus 2x minus 3. And then looking at this, I believe this factors nicely as x plus 1 times x minus 3. And so that's our factored derivative. And then looking at this, this is equal to 0 when x is equal to minus 1 or x is equal to 3. So that's our two critical points for this cubic. Okay. So now that we have critical points, how do we tell if it's a relative maximum, relative minimum, or neither? Right. So a critical point is going to be a relative maximum. Well, so if it's a relative maximum, remember it looks like that around there. So the slope coming in to the left is going to be positive, and then the slope going away, it has to be decreasing going away, so it has to be negative. So for a relative max, The slope at that point is changing from positive to negative. Another way to think about it is if you look at this, this is curving down. So the second derivative, if it exists and is non-zero, has to be negative, right? And so this is saying the second derivative has to be less than or equal to 0. Okay. On the other hand, a critical point is a relative minimum. So let's draw an example of a minimum. Means that as you come in to the left, slopes are negative. They're decreasing coming in. Coming out on the right, the slopes are positive. Right? So the slope is changing from positive to negative. Means that it's a relative min. And then another way to think about it is, what about the concavity? Well, this is curving up. Right? So the concavity is positive. And so this is saying that the second derivative is greater than or equal to 0 at a relative min, if it exists. So let's go back to this function. So we've had critical points at x equals minus 1 and 3. Our f prime of x was minus 3x squared plus 6x plus 9, which could be factored as minus 3 times x plus 1 times x minus 3. So at these critical points, we're thinking about these points. Minus 1, 3. The first derivative at both of them is 0. Now let's figure out what it is on the rest of the number line. So let's pick something a little bit smaller than minus 1. Maybe the easiest thing to do would be to pick minus 2. So if I pick minus 2, plug that into the first derivative, f prime of minus 2, that would be 12 minus 12 plus 9. Is that right? That should be a minus 12 there, right? Yeah. Minus 12 plus 9. And so that's minus 24 plus 9. I don't know exactly, but I can tell you it's going to be negative. So it's decreasing coming into that point. Now I need a point between minus 1 and 3. Easiest one to pick is 0. And it's going to be just 9 there. So that's going to make it positive. And then if I pick something like 4, that's going to be minus 48 plus 24 plus 9. Don't know exactly, but it's going to be negative there. Okay, so looking at this, the first derivative here, it's negative to the left of minus 1. So the function's decreasing there. Positive between minus 1 and 3. So it's increasing in between. And then at 3, to the right of 3, then its first derivative is negative. So it's decreasing again. So at minus 1, it's decreasing going in, increasing going out. And so that's saying this is a relative min. At 3, it's increasing coming in, decreasing going out. And so that's a relative max. Okay. And if we wanted to use the second derivative here, if we take the derivative again, so that would be minus 6x plus 6. When we plug in minus 1 here, that would be 6 plus 6 is 12, which is greater than 0. So it's concave up, which means that it is a min. If we plug in 3, I get minus 18 plus 6 gives me minus 12. And so we can see this is less than 0. And so this is concave down, which means that it is a max. Okay. Okay, so practice problems from this video. I've given you 3 functions. So for each of them, find the critical points. And then once you've found those critical points, similar to what we just did, determine which ones are the relative maxima, which ones are relative minima, and which ones are neither. Okay, see you in WebEx.